Hello, everybody. Welcome to this afternoon's session. We're going to start this afternoon with Morgan Wahl is going to be speaking on text is more complicated than you think, comparing and sorting Unicode code. Let's give him a big hand, please.
Hi. This is my first ever talk at a conference of any size, so wish me luck. Thanks. I changed the title slightly from what's in the program. It's a little simpler. So who the heck am I? My name is Morgan Wahl. I'm a web developer using Django and Python for about 7 years now. I work for an organization called AdGene. We're a library of DNA for molecular biologists. And that's the last I'm going to talk about DNA. I'm a bit of a linguistics enthusiast, and learning all the details of how Unicode represents text digitally, how we handle all the ins and outs of all the written languages of the world in computers, I find really interesting. It's actually a really interesting way to learn about all the different written languages. So, what am I going to talk about? First of all, what is text? What is plain text in Python? We certainly use it all the time, although I didn't even know all the details until I had to write this talk. Some basic concepts in just how we digitize written language. And I'm going to talk about two things you might do with text, compare it and sort it. And specifically when you want to sort it and show it to humans, how to do that in a way that's going to match their expectations and be the least surprising for them. Yeah. I'm not going to talk about all the details of translating your UI, internationalization. Actually, where I work, all of our UI is in English. Most of our users are molecular biologists and like computer science, like Python. English is just the lingua franca. All of the big journals are in English. We just expect our users to know English. That said, we can't act like the world is all ASCII. Most of our users are outside the US. The majority of people who request DNA from us are outside the US. They can type all sorts of stuff that we can't type, generally, the developers. And of course, they can copy-paste anything. So we still have to deal with all sorts of text coming into our system. I'm not going to talk about how to render text, how to go from some representation in memory to pixels on a screen. You'll see why in just a bit. I'm definitely not going to get into how you go about editing that text, the UI for that, even more complicated. And I'm not going to talk about fancy natural language search algorithms. Those are things that are built on top of what I'm talking about. What we're going to go over is just the foundation for all of this. You'd be forgiven for thinking this is a talk about Unicode, because I'm going to talk a lot about Unicode. That's because it's really the standard for representing written language digitally. It's the only real attempt to do that for all the written languages of the world. In the past, we had ASCII, code page 857, a whole variety of encodings where they're generally pretty simple because they would only want to support one or maybe two written languages, and that made a ton of simplifications. That hid a bunch of problems and complexity of dealing with actual written language. And Unicode can't avoid that complexity. It can't avoid those problems. Sometimes people get sort of annoyed that Unicode seems more complicated than ASCII. That's just because text is complicated. If you want to faithfully represent the way humans have used written language for a long time, it's going to be a little complicated. Yeah. So there's actually more than one Unicode. Unicode's versioned. Current version is 9.0.0. Each one you could think of as sort of another attempt to get it right. there's always, nobody's perfect. There's always more things to address. There's even novel ways of writing that have to be added. Most people think of emoji, for example. There's also, the most recent version added Osage, which is a writing system, a script that didn't exist until the 21st century. Unicode has stability guidelines. If you read the standard itself, even though it does change over time and it's versioned, there's specific parts that are guaranteed to never change that you can depend on. There's specific parts that may change, and you need, if you're writing algorithms that deal with that data, you need to know which is which and how to deal with forwards compatibility and backwards compatibility. Unicode, there's the standard itself, which really lays out the basics, like what is a character, what is a grapheme cluster, what is white space? Really fundamental stuff. What's the whole set of all the scripts that we have to support? There's a chapter on pretty much every script that gives you all of the nitty-gritty details of how it's represented in Unicode. And then in addition to that, there's standard annexes and technical standards. It doesn't really matter the difference. The point is these are extra standards in addition to the Unicode one itself that are generally written by the same people that deal with one particular thing. We're going to talk about a few of these. We're going to talk about normalization and also the collation algorithm, which is sorting, basically. They're all pretty interesting. There's also the common locale data repository, which is a separate project. It's sort of the modern equivalent of the old POSIX locales. It's a whole big curated database of how to do things in different written languages. How do you format a number in German versus Japanese? It's its own project because it has a separate, it's kind of its own organization, but you'll see its website is part of the Unicode website. It's a lot of the same people work on both. So, what's text? Text in Python, and really in general, it's a sequence of code points. Code points are ints. They're positive ints. The biggest one is 110,000 in hex. So there's about 1 million of them, a little over 1 million of them. Some of those code points are assigned to characters. Most aren't. The vast majority aren't, as you can see from these numbers. The ones that say 128,000 characters, those are the ones that are assigned. These characters are defined by the Unicode standard, exactly what they're supposed to look like in different contexts, how they're supposed to behave. There's also even more private use characters. These are code points that are guaranteed to never be officially used for anything. They're for you to use for your own whatever you want. If you want to represent Klingon, the Unicode committee has said that they're not going to standardize that. So, but you can still use it. You can use private use characters. You can make a font that assigns glyphs to those characters so you can see it. You can search it. And you can exchange text with other people as long as they have the same assignments. There's 65 non-characters. So these are things that aren't meant to be used for regular text, but they are given specific uses within the different Unicode standards. And there's also the surrogates, which are a backwards compatibility mechanism we're not going to get into. The rest are technically called reserved. A lot of times you just call them unassigned code points. So how do we get to these code points? Well, like anything, we start with bytes. And encoding, the way Unicode defines it, is a way to go from bytes to a sequence of code points and then back to bytes. On the left here, you see there's UTF-8. And there's also UTF-16. The bytes are completely different. They represent the exact same sequence of code points. A sort of pet peeve of mine is occasionally people will say, we need to convert something to Unicode when what they want is bytes. There's such a thing as just Unicode. The standard itself defines 7 different encodings. In general, you have to pick one, and you need to specify what it is. Just use UTF-8. When you find yourself in the situation of needing bytes, UTF-8 will work fine for you. The other ones do exist for reasons. If you need them, you'll know that you need them. Yeah. So code points, they're more than just numbers. Oh, I almost forgot to mention. You can see here there's a typical notation for code points. It's a capital U and then plus sign and then some hex digits padded out to 4. And here I've shown also the names for the characters assigned to these code points to give you a sense of what is encoded there. And we'll see the string in a minute. Code points have properties. So they're more than just this is separate from the other ones. The Unicode standard also defines a whole slew of properties. There's over 100. They don't all fit on this slide. Generally, these properties all exist because there's some algorithm that needs to tell different sets of characters apart. And it's going to do that by just saying characters with this property behave this way, characters with this property behave this way. This is a future-proofing thing where we can always add more characters, and as long as we set their properties right, the algorithm works fine. Oftentimes, the same code will work fine. You can just update your copy of the Unicode character database, which defines all these properties. And in theory, a lot of stuff will just continue working. In reality, if you find yourself implementing an algorithm that needs these properties, you're probably reinventing the wheel. You should find if somebody else has. But it's still useful to know about them, to know at least roughly what they mean. It can help you when you do have some problem you're trying to debug where some particular string has weird behavior, you don't understand why. Understanding what these different properties mean can be helpful. So let's look at a couple properties. Here's name and age. We've already seen name. Age is what version of Unicode it was assigned. 1.1 just means it's old as dirt, really. There's nothing that's 1.0. 1.1 is from 1993, so some of these assignments are older than people here, probably. You can see there's another, taco got added in 8.0. Also, notice the stability of Unicode names. There's a typo in one of these names, but that is the official name, and it will never, ever change because the names are guaranteed to be stable. They will never, once a character is assigned, its name will never change, even though it's called a brat cat. Another property is general category. This is a stand-in for when we say letters and numbers. In regexes, when you define character classes as digits, this is how you pick which actual characters you're going to match. Again, these are open categories. New characters can be added in later revisions of Unicode, and when your regex engine updates its sort of own little copy of the character database, it will work with those new assignments. And they're intentionally structured so that there's a general category and then a more specific one for most of these. So all the letters have a letter category, and then they're also subdivided into uppercase and lowercase and other. Here's a good example of a property that's really boring, but it's very important. The case folding property. This tells you, case folding is something we're all familiar with. I'm going to talk about it in depth more later, but the point here is the value of the property is just another code point. And for all of these, except for the first one, it's the same code point. You can write a pretty simple case folding algorithm by just taking this data and saying, replace it with its case folding property. And that will mostly just work. All right, so we haven't actually, you may feel like we haven't actually looked at these strings yet. And that's because you don't really see characters. Characters, these abstract things. Unicode gives them a very concise, if somewhat philosophical definition of, I can't even say it all right now, but essentially it's, if they make a meaningful difference, then they're separate. If it doesn't matter that they look different, then they're the same, but they always mean the same thing, then they're really the same character, and it's just two different glyphs. In general, characters are what we deal with in text. When you search through a document, I don't mean like a fancy search, like just Control F in a document. You're searching the characters. You don't care what the fonts are in your matches. You don't care whether it's italicized, how big it is. That's all font stuff. That's all glyphs. Fonts are essentially a bunch of glyphs and information on how to map from code points to those glyphs. Here we have some actual glyphs now, finally. Each row is the exact same sequence of code points. Each column is a font. As you can see, rendering is not perfect on the Pinyin script one, also Mengal. The accents aren't always put in the right place. And more obviously, most fonts don't have glyphs for most characters. You usually don't even notice, because rendering systems, which are very complicated, have fallback mechanisms where if they don't have a glyph in the font that they normally use, they look for another font that does have a glyph. And if they totally give up, different ones do different things. They might just put in a box, it might not do anything. That varies. But generally, if somebody sends you something and you can't see it, it's probably because you don't have a font with a glyph for it. Like rainbow flag emoji here. Pretty new character. I actually had to take a screenshot to put it in this table because it doesn't work on my browser, because I don't have a font. All right, so text rendering. Here's 7 code points. When you render it, and this is blown up to show detail. When you render it, a user might say there's only 2 things there. What users think of as characters and as letters is very different from code points. This is one of the many things that makes rendering complicated. You can see here also, the first code point is lowercase o. After that is what's called a combining character. It's just modifying the character before it, the base character before it. You can have whole sequences of combining characters. They all modify whatever base character came before that whole sequence. We'll see more examples of that in a sec. After that space, there's also those 4 code points give you rainbow flag emoji. Why is it 4? Well, first of all, there's waving white flag. White actually is a typographical term here. It means the color of the background. So if it was laid out on a black background in white text, it would be a black flag. But essentially, it's a flag symbol, a character called a variation selector, which is kind of a sort of special combining character that, for most of you, you can ignore. Unless you're writing rendering software, you can ignore this. But it's requesting that the character before it be given an emoji representation. Usually means color instead of black and white. There's a 0 width joiner. This is a character that, it's another kind of formatting character. It's saying the 2 base characters on either side of it, try to mash them together when you render this. In that case, it's a white flag with an emoji styling and a rainbow. You stick them together, and this is a standardized thing. You stick them together, and you get a rainbow flag. It's done this way partly for backwards compatibility. If you don't have a glyph rainbow flag, you can actually end up with a flag and then a rainbow, which you can kind of piece together what was meant, instead of just a box or whatever the fallback your rendering system uses. Yeah, I picked this example because it's particularly complicated. And you can see why we're not getting into the details of text rendering. This is also why you should not implement text rendering yourself. It may seem like it's simple. You look at the code points, you put some images next to each other. It's always much, much more complicated. Just don't do that. Unless you work on one of the libraries that do that, in which case, thank you very much, because it can get very complicated. So some actual code, finally. This little function I'm going to use a few times to help us look at a string in Python and see what are the actual code points in there. At the bottom, it's showing hello world emoji. You can see in the implementation, I'm importing something called Unicode data. This is actually in the standard library. It's not the whole Unicode character database. It's a little slice of it that Python needs to implement a lot of the standard library features. And it's also available for you to use. If you want to know what version of Unicode it's based on, there's a property on there to tell you that, an attribute on there to tell you that. So yeah, and that's where we get the names for each one. And so you can see in the output of this function, it's 1 line per code point, and at the bottom you have the string itself rendered. So this can be confusing. Remember, what you see is just glyphs. It's not code points. These 2 strings look totally the same. They compare not equal because they're different sequences of code points. So what's going on here? Remember I said you can have multiple combining characters after the same base character. If those combining characters are in the same spot, so to speak. If they all go on top of it, they'll just stack up as you add them on. And so the ordering is significant there. If one's on top and one's on bottom, it doesn't really matter the ordering. You can say E with a circumflex accent and a dot below. There's some rendering fails here, but the meaning is the same. You can say E with a circumflex accent and a dot below, or you can say E with a dot below and a circumflex accent, and it should always mean the exact same thing. There's no semantic distinction here. Unicode calls these canonically equivalent. Basically, we understand that by having combining characters, it's possible to have two sequences of code points that mean the exact same thing, even though they differ. There's also a few characters that shouldn't have been encoded, but are. Generally, this is because Unicode does have a requirement that anything in a legacy encoding has a one-to-one mapping to a Unicode character, even if that legacy encoding doesn't have this nice thought-through definition of what a character is. So some legacy encoding made angstrom sign a separate character from just A with a ring. Even though that doesn't really make sense, we don't have characters for meter sign, it's just M. You just use lowercase m. So Unicode encodes it, but it has a canonical decomposition, which is basically saying it's always exactly the same as this other sequence. In this case, a capital A with a ring above it. So how do we actually deal with this in code? If you want to compare strings and actually get if you want equals to actually give you something that makes sense to you, and even when they look the same, the way we do that is with what Unicode calls normalization. There's two different normalization forms. Basically, normalization is an algorithm. You hand it a string, you get another string back. Most of the time, you get the same string back. If you hand it something that has a canonical decomposition, you get the decomposition back. There's two forms. I'm not going to get into the difference. I'm going to show normalization form D, because that's simpler to understand. Normalization form C is the one you should actually use if you're doing this. Some rendering systems deal with it a little better if you're storing the strings that you get from this algorithm. So here you can see, on the left side, we have the same sequence E with a dot and a circumflex. We hand it off to the normalize function that's from the standard library. We have to tell it what normalization form we want, NFD, and we get a sequence out. It's exactly the same. On the right side, we have the combining characters switched. When we normalize, it switches them back. The particular order it picks doesn't really matter. It's arbitrary. The point is, if they're canonically equivalent, then you get the same thing out when you normalize. And then you can compare these, and they'll compare equal. Same thing with something with a canonical decomposition. By the way, if you haven't seen this syntax before in Python, where in a string literal, you can do /N. I didn't even know about this till recently. And then in curly brackets, you put the name of the code point, like the name Unicode assigns. That's the same as saying /u, and then it's code point in hex. Only it's a little more readable, although a lot longer. So anyway, so we take angstrom sign. You can see it's just this one code point. We normalize it, and we get the canonical decomposition. If we compare this to a string that's A with a ring above it, they'll compare equal once we normalize it. There's another sort of flavor of normalization called where we do compatibility decompositions. These are more characters that they're in Unicode, even though they don't fit the definition of character, mainly because some legacy encoding said they were separate. And we don't want to break existing systems. But we still want them to use Unicode. These, when you change them to their decomposition, you can lose some meaning, potentially. In this case, we have a superscript 5. Unicode recommends you not use the superscript characters. If you want superscripts, use HTML, use a higher level thing. You can't nest them like this. There's all sorts of problems. Just use HTML or text or MathML, whatever makes sense for you. But if you had existing data with this in there, you wouldn't want to just convert it to 5, because then you'd be losing information. But if all you care about is equivalence, if you want to just say, this is basically the same as 5 to me for my searching purposes, or whatever you're using comparing strings for, You can do that with normalization. You'll get its compatibility decomposition. So should you pass strings to normalize every time you want to compare them? Probably not. That would be really tedious, even if you abstracted it out. What you really need to think about is, well, why are you comparing them in the first place? Can your database just do this for you? If you have a text search engine like Lucene, or that's what Elasticsearch uses, or Zapier or Whoosh, check in its docs. Does it do this normalization for you? It really should be. The main thing, though, is why are you comparing it? Most of the time, it doesn't matter. You don't have to normalize. A lot of times when we're comparing string literals in actual code, we're doing something like this. We have a dictionary. The keys are some internal values that we use. Maybe we use them as values in a database. And then the values in the dictionary are strings that we show to users. And we're just doing a lookup. These are just literals in our code. We don't need to normalize them. We know they're always going to be the same. We don't need to worry about it. If you're doing like a quick and dirty, you just need to search through a bunch of strings. Then you may want to consider normalizing, although you've started implementing a text search engine at this point. So you should look into just using one of those instead. If you want to do something like, say, make sure usernames are unique, think about why you want to do that. Most systems, they end up restricting usernames to a certain set of characters, specifically because there's lots of different glyphs that look alike in different scripts. If you look at internationalized domain names, it's this problem in spades, and it's very complicated to solve. All right, case folding. This is something we're all familiar with because ASCII does it. Case folding code is littered throughout software. From a Unicode perspective, there's simple case folding, which is what Python 2 did. The length of a string never changes. You always replace one character with another character. And we're just talking about folding. When we just want to ignore casing distinctions, we'll fold the two strings together, and we'll expect to get the same string if they differ only on casing. Python 3 actually has what Unicode calls full case folding. So you can see a few characters actually get a little longer. This example is used in German, but it's used in the word for street. So you could very well, if you take addresses, you could very well have this character in your data. Python 3 also adds a nice case fold method that is separate from having to pick lower or upper, that there's certain edge cases that it handles correctly. Python 3 regexes still do the simple folding, unfortunately, apparently. All right. In general, casing isn't specific to a language, except Turkish. If you have a bunch of text that's Turkish or Azuri, there's a few other languages that do this, you have to case fold it a little differently if you want to match users' expectations. It's not too complicated. I mean, you can see the implementation right here. Essentially, I with a dot is treated as its own thing, whereas everyone else treats the dot on a lowercase I as this weird optional glyph thing. All right. I mentioned in the talk description there are over 1,000 Latin letters. Here they are. Actually, that's not quite true. A few of these are numbers. So let's color the numbers blue. And the rest are all letters. Now, a lot of these are canonically decomposable. They're basically in there for round-trip compatibility with legacy encodings. So let's have those just disappear, because we don't really care about those. A lot of these are compatibility decomposable. So let's just gray those out, because they don't really matter that much to us. All right. Now, this is something kind of approaching all the Latin letters. It's a lot more than you might expect. They might look kind of strange, but they are still, a lot of them are letters that you can recognize. You know, it's like a D with a funny curlicue on it. Here, we've ordered them, assorted them a little differently to make it a little more obvious what's going on here. You can see there's a B, and then there's all the different variants on B. All the way down, and it's sort of the ordering you'd expect. even though you don't even recognize a lot of these, this ordering is a little more intuitive than this one. This one is code point ordering. You just look at the code points, compare them as integers. Code point assignments are just an accident of history. For English, it's kind of annoying to use them for sorting. For other languages, it totally makes no sense to users whatsoever. Whereas this ordering actually is kind of intuitive and useful. That brings us to collation. And this is sorting specifically for display to humans. If you just have an algorithm where sorting is a component of it, it doesn't really matter how you sort. You can sort by code point, that's fine. If you are showing a bunch of text to humans in your UI, and you need to put it in an order of some sort, this is how you should do it, for people to be able to find things in it. Sorting is sort of old school search before there was computers. In general, you should use search to find stuff. But that can be hard. It can be hard to implement in whatever use case you have. So a lot of times you do still end up with, OK, I've narrowed it down to this data. Now I need to show it to someone. And I need to show it to them in a way that they can find what they're looking for themselves. So there's the Unicode collation algorithm. By default, it defines a pretty nice ordering. That's what you saw on that previous slide. Collation, believe it or not, varies a lot, how exactly you want to do it. It varies by language, of course. Even within a language, it can vary. German has 2 different orderings for phone books and dictionaries. And even for individual users or individual programs, it can vary. You may have a preference about whether numbers come before letters, whether uppercase comes before lowercase, or if your user only uses Hebrew, they probably want Hebrew to come first and not Latin. So the UCA, in addition to a nice default ordering, has a nice mechanism to define tailorings of that, which is basically you're taking this existing thing, which was a ton of work to come up with, and you're just tweaking it to get the ordering you want. In Python, well, first of all, look at your database to see if it does this for you. Because that's a great place to be sorting text. It's probably going to be faster than doing it in Python. If you do want to do it in Python, there's a nice library called PyUCA by J.K. Tauber. It's simple. This is the API on the slide. There's no way to really tailor it, though. It does work nicely, though. Short of, you can give it a new data file where you have to define the ordering for everything yourself. So that's not so great. But when you just want to put things in a better order than code point order, this is great. On the left here, you see punctuation is kind of scattered around how it's handled in sorting. When this is using just code point ordering. On the right, you can see we're using PyUCA, and all the punctuation gets at the top. All the single quotes are next to each other. It's a lot more intuitive. So let's look at some casing distinctions and also accents on characters. What is the sort order you would want these to be in? Is it that? Because that's a really nice sort ordering. That's a really great collation. If you want to know whether a particular string is in that list, it's so much easier when you look at the list on the right. Getting there is a little complicated, though. And in order to do that, it's not just a matter of defining a sort key. We need to define a multi-level sort key. And that's what UCA does. Essentially, we're saying we're going to look at the most important differences first. We're going to ignore case. We're going to ignore accents and other things. And if 2 strings are the same at that level, then we're going to look at the accents and use that to distinguish them. And if they're still the same, then you look at case, and you fall back on looking at invisible control characters if you have to. So in general, when you hand a UCA implementation a string, what you get back is basically a tuple of ints called weights. And then that tuple is what you then hand off to your actual sorting code. Here you can see A gets a primary, secondary, and tertiary weight. And when you concatenate the 2 strings, the weights get interleaved. You can't just concatenate those sort keys together. You have to, when you have a new string, you have to ask for a new sort key. And this is how we get that nice ordering, because we're looking at the primary weights first. So let's look at actually customizing this collation a little bit. It's not easy to do with PyUCA, but we can with the Python bindings for the ICU library. I don't know if you've used the ICU library before. It's sort of a behemoth from the C++ Java world. It does have Python bindings, though. You can install it with pip. You have to set a weird environment variable, but it's doable. There's the API documentation for Python. It doesn't have any. It tells you to look at the C++ APIs. So that's not great, but it does do a lot, and it's very useful, despite its API in Python also being very ugly. Here you can see we've made a collator. It's going to give us keys. And here we've customized it a bit. We've told it punctuation. We've essentially told it punctuation matters to us less than everything else. And that's how we get this great ordering where those quotes don't matter until it's a last resort. So the word punk gets sorted right after punk in all sorts of quotes, which is pretty nice. All right. So there's one more sort of caveat to using the UCA. And that's if you have tabular data. You can imagine this as a tiny little slice of a database. Really, anytime you have tabular data. Oop.
Another sector of the building has reported a fire alarm condition. Management is investigating. Please remain calm where you are. Please wait for further instructions.
Okay.
Otro sector del edificio ha reportado alarma de incendios. La gente está actuando.
Okay. Well, we only have 5 more minutes, so I'm just going to keep talking. Oh, great. All right. Okay. Anyway, when you want to sort these, like if you want to do first sort by column 1, then sort by column 2, you can't just sort by column 1, then 2, because you're going to end up with what you've said were minor distinctions in the first column, like accents and casing. They're going to swamp out more important distinctions to you in the second column. Here, we want Fred and John to be next to each other, because the first column only differs by accents and casing. So, yeah, so here's why that's happening. You're essentially looking at third-level weights in that first column before you're looking at first-level weights in the second column. What you want to do is merge them together. Look at the first level weights in the first column, look at the first level weights in the second column, then look at the second level weights in the first column, and so on. So how do we do that? Well, it's kind of like when we concatenated strings before. So maybe we can concatenate them together. That doesn't actually work. It gives you a nice ordering, but it also gives you a confusing ordering where the shorter string got put after it. So the CLDR defines a whole bunch of stuff. If you remember, I said it's like a big database of locale data. One of the things it does is it has its own default ordering that improves on the UCA a little bit. One of the things that does is define a weight for this special code point, FFFE. This is a non-character code point. It shouldn't ever occur in text. It's to use specifically for stuff like this. And the ICU uses the CLDR data. So its default collation is the CLDR one. So if you join those strings with that special code point, then you finally get the ordering you want, where you're getting the first level distinctions on both columns. Right. And that's it. I believe I have, what, a minute or 2 for questions, if you want to talk over a fire alarm. Oh. No questions? Okay. The slides will be on SlideShare under the PyCon 2017 section, and my references are all on the last slide. Thank you.
Hello, everybody. Welcome to this afternoon's session. We're going to start this afternoon with Morgan Wahl is going to be speaking on text is more complicated than you think, comparing and sorting Unicode code. Let's give him a big hand, please.
Hi. This is my first ever talk at a conference of any size, so wish me luck. Thanks. I changed the title slightly from what's in the program. It's a little simpler. So who that guy might? My name is Morgan Wahl. I'm a web developer using Django, Python for about 7 years now. See natural language search algorithms. Those are things that are built on top of what I'm talking about. What we're going to go over is just the foundation for all of this. You'd be forgiven for thinking this is a talk about Unicode, because I'm going to talk a lot about Unicode. That's because it's really the standard for representing written language digitally. It's the only real attempt to do that for all the written languages of the world. In the past, we had ASCII, code page 857, a whole variety of encodings where they're generally pretty simple because they would only want to support 1 or maybe 2 written languages, and that made a ton of simplifications that hid a bunch of problems and complexity of dealing with actual written language, and Unicode can't avoid that. I work for an organization called AdGene. We're a library of DNA for molecular biologists. And that's the last I'm going to talk about DNA. I'm a bit of a linguistics enthusiast, and learning all the details of how Unicode represents text digitally, how we handle all the ins and outs of all the written languages of the world in computers, I find really interesting. It's actually a really interesting way to learn about all the different written languages. So, what am I going to talk about? First of all, what is text? What is plain text in Python? We certainly use it all the time, although I didn't even know all the details until I had to write this talk. Some basic concepts in just how we digitize written language. And I'm going to talk about 2 things you might do with text, compare it and sort it. And specifically when you want to sort it and show it to humans, how to do that in a way that's going to match their expectations and be the least surprising for them. Yeah. I'm not going to talk about all the details of translating your UI, internationalization. Actually, where I work, all of our UI is in English. Most of our users are molecular biologists and like computer science, like Python. English is just the lingua franca. All of the big journals are in English. We just expect our users to know English. That said, we can't act like the world is all ASCII. Most of our users are outside the US. The majority of people who request DNA from us are outside the US. They can type all sorts of stuff that we can't type, generally, the developers. And of course, they can copy paste anything. So we still have to deal with all sorts of text coming into our system. I'm not going to talk about how to render text, how to go from some representation in memory to pixels on a screen. You'll see why in just a bit. I'm definitely not going to get into how you go about editing that text, the UI for that, even more complicated. And I'm not going to talk about fancy